Cool, thanks, Tom. Yeah, I'm the developer of GLVisualize, and I've selected a few GIFs made with GLVisualize to give you a first impression of what you can do with it. These stutter a bit. In GLVisualize, obviously, they wouldn't stutter. That's just the presentation. Today, I want to tell you a bit about my motivation behind GLVisualize. Then a quick overview over the features of GLVisualize. And then I want to show you a few new features that I have in some branches in GLVisualize. After that, a quick demo. And then I want to give an outlook into the future, what you can expect from GLVisualize in the near and far future. So I have this very abstract motivation for writing GLVisualize, and I try to put it into this Venn diagram here. So as you can see, there's high performance computing in one circle, art in another circle, and data science in another circle. And I've pretty much worked in all of these areas for a while. And so I know the disadvantages and advantages of these areas. So in high-performance computing, for example, everything is made really fast and everything has low latency, and this is really great, but the usability is really lacking usually. And then there's the area of art. I've worked with Photoshop and 3D Max a lot when I was younger, and it's just so awesome how you can just take data, edit it, interact with it, and make really nice looking things out of it. But as soon as you start scripting, I think things get a little bit more difficult there in this area. And then there's data science, where you have a lot of tools for filtering data, scripting data, plotting data programmatically. But it kind of falls apart as soon as you want to edit your plots and work with them interactively. So I'm a big fan of the sweet spot here where everything is really fast and interactive and really easy to script. And that's what I'm on an abstract basis aiming for. And for that you need a platform. So at some point I had to decide, where do I want to implement GLVisualize? And the first point is ease of use. I really want to be able to quickly prototype, write functions really quickly, and try out new things. But on the other side, I always think you will need C call. You need to be able to call all these C libraries, because there are still so many of them and they're all awesome, and you don't want to reinvent the wheel there. So that's a really important thing, and it should be without it should be with low overhead, because otherwise your things will get slow in the end. And I think number crunching and machine learning are really fascinating areas which most of the apps of the future will probably use in one way or the other. So I really want to have this immediately accessible in the platform of my dream. And of course, a graphic engine to visualize all these kind of different things for whatever reason. So this probably sounds a lot like Julia to you guys. We all have it there, and we can even write a graphics engine, and it's reasonably fast, and the GC is not making it stutter, which I didn't expect actually, but it seems to be working. So the other question is why I'm fixed on one language. I mean, you could just use multiple languages, one for the data science part, one for the visualization part, one for whatever part you're interested in. But I think it's always a compromise for your idiomatic code. For every language you have different sets of idiomatic code. You need to kind of switch between them, and the more idiomatic code snippets you have, the harder it gets to manage them in your mental model, I think. And also each language has its unique set of problems. And if you're really unlucky and take like 3 languages, you get the union of all problems of the language, which would be really bad. I think. And on the last point is, I mean, it's a lot easier to control one language and make everything fast in one language as long as the language allows it to make things fast, instead of doing optimization across language borders. So that means I wanted to really do something in one language, and I chose Julia. That's how GLVisualize basically started. So GLVisualize is, as I said, written in Julia. The whole one language thing didn't work out that well because you need OpenGL to run things on the GPU. So that part is written in OpenGL, the OpenGL shading language, but the rest is all Julia. It's optimized for large data sets and animation, so it should be really easy and straightforward to animate something in GLVisualize. And I've come up with this very simple API for GLVisualize, which is a bit like a show method in the end. So it always has just one argument and dispatches on the type to decide what default visualization it should choose for it. Then you have an optional style argument, which can switch between completely different styles. So for example, if you have a matrix of floats, you could switch between having it printed basically as a textual representation, or have a height field, or have a bar plot of this. This would be done with the style keyword. And then you have the keyword arguments, which are used to customize every single parameter of the visualization. And you can pass styles, signals for any of these arguments, and signals then just means that it's animated in the end, the parameter or the whole data. And very similarly, I have this widget function, which is still called differently, but I think that's probably the name to go for, which takes the signal and returns a widget for it so that you can display and then edit the signal basically. So the signal could be a Boolean signal, and then you have a button basically. You get back a button for that. And you can customize it with different images for the button. So that's my way of doing UIs sort of. It could be a color, then you get a color chooser basically. And then there's this place function, which places a visualization in some area of your space. This could be 3D or 2D. And could also be animated as well, of course. Recently, I've implemented a lot of new features. For example, anti-aliasing for the 3D plots. It looks a lot better now and isn't even that much slower, which is good.
Which one is right?
Yeah, this one is the without anti-aliasing. You see the little saw here, and it's a lot smoother. I mean, this is zoomed in, so if you see it in the real resolution, it looks a lot better. And I finally got around to implement transparency. It's only approximation, but it works fairly well for an approximation. And yeah, this exists now in a branch. I have a few problems with it because that's basically how this looks if you implement these kind of new features. So the order-independent transparency interacts badly with some visualization types, for example, the line types. Or some things are a lot slower suddenly. And then the FXAA interacts with the font rendering a bit. So yeah, it's hard to really get performance and quality at the same time. So probably the way to go is to have a very easy way for the user to actually define the preferences if they want to have more performance or more quality in the end.
I know it's a loop, but I just really want it to converge.
Yeah, right? Well, it's not that slow if you, even with the highest quality, it's. So I've added this multi-line type, where you have just a matrix of points, basically, and every column is one line, which is not such a new feature, but it's a lot faster than drawing a lot of different lines. So you can I don't know, you can actually draw a couple of millions of these line segments now with that. So if you have particles and want to visualize the trail, this is the one to go for. And I finally added vertex column meshes with wireframes. That took a long time, but it's actually quite easy in the end if you have line renderings. Oops, there we go. I have prepared a demo, real life, with a few bugs. I will try to work around that. So this is basically the new glplot. So glplot is just, in the end, now a very thin layer over GLVisualize, which gives you some UI elements, like these little buttons here. So now I can, for example, center the camera like this. This is new. And I have this little cube here to fixate on the edges, basically, on different direction of the camera space. And I can switch between orthographic and perspective projection like this. Yeah, and I think this is also, this cube here is a good example why it's good to have the plotting API together with the UI API, because you can do these fairly complex UI elements, which are basically 3D objects with which you can interact. And these are screenshots buttons and video record button. Actually, with the projector connected, they don't work right now. But usually they should. And I have this play button here to play this little animation here with a slider. And I have this new menu bar where you can blend out the animations and actually also edit them if you want to. So this is this ISO field plot here, ISO surface plot of a volume. So you can go through the ISO values pretty easily. And these menus here, these are basically the parameters that you could otherwise pass to the visualization function. So these are now signals and animatable already. Same goes for the color. You can just change the color really quickly. You can blend it out. And actually, I've implemented this little gimmick to show you that you can even do fairly complex operations, like editing a mesh, like this. So for example, if you have a simulation where fluids flow around an object, you could just update it online and see how the stream of fluid changes while doing this. I think these are very compelling use cases in the end. Probably not in this demo, besides making this cat more ugly.
We have cool feet animal laws in this country.
How do you know which control is controlling which object?
You mean here, which one refers to which object? Yeah. So that's a new feature that will be added very soon. That I will make little icons with a preview of the object. I think that would help. And I have a even more fancy control here for the color map. So you can just change the color of the whole color map per channel, basically, which could be pretty nice.
There's something strange with the numbers on the axis. Is that because of you?
I guess. It's a very early prototype in that sense. Yeah. Okay, I think that's it for the demo. Or do you want to see more interaction? Would be really nice to interactively edit the grid and labels as well. That's very close on the roadmap.
What about 3D selection of points is a challenging operation to implement?
Oh, I do that for the mesh editing.
The mesh editing, okay, yeah.
I mean, that's selecting of a point.
Scatter plot, from your scatter plot, you can do that too?
I can do, yeah,
Okay.
of course. And I can also display the values of that.
And are you updating the underlying data array, or is it just changing the visualization? When you
That's directly on the GPU, actually. I write to the GPU buffer directly. Yep. Any other questions? Yes?
Take your example that you were updating a CFD computation there. How would you propose to change this signal into another? I mean, what kind of data types would you get that? What would be the interface to your calculation program?
I'm not sure if I fully follow. So if you have a simulation, you say, and a signal,
Yeah, let's say you are running a computational fluid dynamics analysis and you are giving on a vertex there, changing the geometry.
so you have two ways, I think. One way is having a signal, just of the whole data, or you can actually directly write to the array of the data. And that is exposed as a GPU array, basically, and you have a few operations defined on that. Could be slow, could be fast, depending on what you do. If you write a loop over this array and access the single elements, it will be really slow. If you update parts of it in a batch, that will be really fast. So depending on your use case, if your simulation updates every data point anyways, your signal will be totally fine and fast. Hope that answers the question. Any others? I think we need to move on anyways. So coming to the outlook, near future, that's stable UI interface would be really nice, because for this demo I've written up a lot of functions, new functions for toggle buttons, and these kind of things, and they are just in one file and not exposed, nothing. I should just write it up, document this, and put it out there. And the compile times are really terrible for GLVisualize right now. It feels really bad starting it up. So if you just want to plot something really quickly, you probably won't choose GLVisualize because it just takes too long. So it would be really important to put it into the user image and actually completely compile it to binary. And there's also an efficiency problem right now with the render loop. So I'm rendering way too many frames. If nothing changed, I'm still rendering frames repeatedly, which feels quite heavyweight. Your laptop gets warm and your fan will start crying. That needs to change, and there are plans for that. And I want to work with Tom Breloff together to make a really nice plots.jl integration. I think that would be profitable for both of us, pretty much. And I've almost integrated the fire render backend, which is a ray tracer. You can see two example images here. So that would offer incredibly high image quality, and actually not only approximated transparency, but real transparency and real volume renderings. It's very powerful and very slow, but I guess it had its purpose, definitely. And I've been working on text placement a lot lately and layouting, and combining text elements with sliders and color choosers. I don't know if you realize that, but in Julia Base there's a complete markdown parser in there. And it's really easy to actually write a new render backend for the markdown. So with that, all these widgets I have in GLVisualize, it would be pretty straightforward to make an interactive markdown renderer in GLVisualize. So it could look like this, that you have this table with these variables, and these could be slidable, and these could be actual color choosers. And then you have the visualization of that data set right besides it. I think that would be a pretty cool use case. And for the farther outlook in the future, I think there are a lot of great backends out there. So there's WebGL, for example, as an alternative to OpenGL, which is definitely really has a really good use case for putting things into the web. And there's OpenGL and Vulkan. Vulkan is pretty new and has a lot of advantages for speed. And probably you can compile Julia to Vulkan directly for the GPU and things like that. And then there are PDF for printing. There are a lot of cool backends, basically. And there will always be new backends. So I felt like we should really try to reuse code as much as possible and write actual libraries that are not backend dependent, especially for graph layout and layouting in general. This is really important because this is not backend dependent at all. But what that means is you need some intermediate representation because, yeah, you need to emit something for the graph layout, for example, if you don't put it directly into a backend. And so you need to have ways to represent lines, points, and surfaces and all these things. And that's how I came to the visualization intermediate representation that I'm prototyping on. GLVisualize basically uses a very small prototype of that already internally. And it's just a mixture of geometry types and functors that you put into them. So for example, you could have a geometry type like a mesh, and then you could have a functor that you apply for every vertex and then generate a color for every vertex, basically. In this way, it would be pretty flexible and composable in the end. Yeah, and you have a lot of constraints on this visualization IR because you don't want to write all these packages that emit this intermediate representation if in the end it turns out this visualization IR is too slow or not generic enough, because then all your packages that you wrote for them will become less worthy. So that's why this is for the far future, because I'm guessing that it will need a lot of design work and trying out. And then you probably even want to compile things for the GPU of this visualization IR directly so that you can use the same data types on the GPU. And you might want to distribute it in different servers or something like that. And it should work there as well fairly fast. Yeah, and that's the third time I mention it, compiling Julia to the GPU. I'm really excited about this prospect because it makes a lot of things a lot easier for me and for the user. As I said, you could just pass user-defined callbacks for coloring per pixel or per vertex or per height in your height field, and you could this way get a lot more usability out of this if you have a special use case. And the backend code will be so much more concise if we could write it in Julia. Right now I'm writing it in this OpenGL shading language, and I could go on a 3-hour-long rant about it. It's really terrible. It's not composable at all, and you lose so much expressiveness. And I write the same function over and over again because I can't really template anything and don't have any higher language like constructs. So that would also be great for that. And of course, debugging. In OpenGL, there's almost no debugging. You can't really debug your shader code. And if you would actually write it in Julia, you could just execute it as Julia code and then have the same debugging capabilities as that. Or Vulkan actually offers a lot there as well. Yeah, that's so much for this talk. The Vulkan talk will come right after.
Are you doing like art? You're going to get off the stage and then come back?
Yeah, of course. There's no way around that.
Questions?
Yes?
Is there a way to export these images directly to a file like a PNG or a PDF?
So the question is if there's a way to export the images. Yes, that works. I wanted to demo this, but with the projector it didn't work. You can just export it as a PNG. Yeah. Yes?
How do you display text? Is there some existing library for that, or did you write it from scratch?
So the question is, how do I display text? I almost read it completely from scratch. So I use signed distant fields. And Yuri sits right there. He wrote the signed distant field package, which I'm using for that. And then I've written my own shaders for that. And I'm using FreeType to load the fonts. Yes. Yep.
How many points can you visualize? So I would like to throw away some maximum so I make it very easy.
How many points can I visualize with GLVisualize? So I think I've benchmarked this on my laptop, which has an Intel HD 4400. And I think the most I could do was 3 million, something like that. It depends a bit. That's actually one of the performance hits I took for the anti-aliased, nice-looking round points. They took a large hit.
Yeah.
But I also have this other really simple point visualization, which is basically as fast as it can be. Yes?
Related to that question, you mentioned that you could use a signal to pass information into the visualization algorithm. How many points per second could you stream in from an external data source?
So the question is, how many points could I stream when I'm visualizing it? That's a good question. I think at one benchmark it was 50,000 around that. So, but that's on my Ultrabook. I should do this with a better GPU and see how that goes. Well, that's I/O bound, basically. Yes?
So going back to the manipulation of the points, and when you're, I assume there's callbacks involved. Is there a lot of communication between the GPU and the CPU? And are you using CPU-based callbacks on that stuff?
Yeah, so how that works is you have a callback for the mouse, and you can see which object it selects, basically, and you can define a callback for that. And then in that callback, you can pretty much write directly to the GPU if you want to, and that's a communication with the GPU. It's not solved that nicely yet, to be honest, but it works fairly well.
And is it expensive to go back and forth between CPU and GPU?
Define expensive. I mean, it works well for these small use cases. But you could update the fairly large buffer every frame on the GPU.
Yeah.
So that's a similar question with the point updates, basically. It works the same way.
Anything else?
Oh. With Vulkan. Yeah, so this talk is about Vulkan. I'm Simon Danisch. And I've been working on wrapping Vulkan together with Oscar and Valentin. Vulkan is by the Cronus Group, if you know them. They also made OpenGL, basically, if you can say so. Today, I'm talking about what Vulkan is, then the intermediate representation that Vulkan is using, and then some pros and cons of Vulkan, why you would use Vulkan in the end. So yeah, it's a API defined by the Cronus Group, and it's a programming interface for the GPU graphics and compute pipeline, which is pretty unique, because usually you just have either one of these in one pipeline, one interface. It could be said that it's the successor of OpenGL, but considering that it's a lot lower level than OpenGL, it also is a new area pretty much. So OpenGL still stays relevant, but everything that was possible in OpenGL is possible in Vulkan pretty much, and it's a lot more modern. And you have pretty much full control over the GPU. I think there are not that many other APIs that give you so much control over it. You can directly talk to the hardware accelerations like the rasterizers. And it has this intermediate representation, which is called SPIR-V, which is the intermediate representation for the kernels that you execute on the GPU. So it's basically a solution for taking away work from the driver implementer and allowing for more languages to actually compile to the GPU. That's the case SPIR-V is supposed to solve. So as you can see, in the history, it was pretty much like OpenGL shading language. Every vendor had to implement their own parser, their own compiler for it, and every vendor did this work. So that wasn't really optimal. So how it is nowadays with Vulkan is that Kronos basically wrote a GLSL parser and a compiler to SPIR-V, and then all the vendors only have to write one driver that executes SPIR-V, which takes away a lot of work and makes it a lot easier to have the same behavior in the end. And as you can see, SPIR-V is relatively similar to the LVM intermediate representation, so that you can convert LVM intermediate representation to SPIR-V and the other way around. So this way you can actually convert SPIR-V to LVM IR, do optimizations there, and convert it back. Or if you're coming from a language that actually emits LVM IR, it should be fairly straightforward to emit SPIR-V from that as well. So OpenCL goes this way up from version 2.1, that it actually uses Clang to compile the kernels to LVM IR and then emits SPIR-V from that. And this other language here, this might as well be Julia. So there are these two ways we could compile to SPIR-V. And there's this one way that you could go from LVM IR and convert that to SPIR-V. Tim Bizarre and Valentin Shiravi work on this. They work on the CUDA part of this, but it should be relatively straightforward to apply the same things to SPIR-V as well. And then code, you could go also from code typed in Julia and emit directly SPIR-V. Oscar, he's up there, he wrote a little prototype for that. That's actually working already for very simple cases. And that would actually make this, these user-defined callbacks that you can execute on the GPU a reality that I was talking before. And I don't know if many people realize this, but calling functions on the GPU, these kernels, incurs a large overhead. So what people do that offer generic interfaces for GPU programming is usually they write their own JIT compiler to fuse functions together so that they can eliminate this overhead. And they write their own, and if we have this framework going, we don't need to write our own because we already have a JIT compiler then. We could just use Julia's metaprogramming capabilities to do these kind of optimizations, which I find really cool. So what are the pros? Why would you use Vulkan? Well, first of all, there's actually a large support from the industry for Vulkan. All the major GPU vendors have an implementation for it. And there even Google and Microsoft support it fairly well. And it comes with a driver. So if you have a GPU that is compatible with Vulkan, it is will be already installed on your computer. So that's different from OpenCL and CUDA, for example. You would need to install that, and I don't know if you've done that. It can go wrong, basically, installing CUDA, or can steal you a couple of hours of your time. It's very high performance, of course. That's what you get if you get a really low level. And it has a way better memory interface than OpenGL. So this question with updating the GPU data interactively, I think this will be a lot nicer. And you could even do it in parallel. That's not really that easy in OpenGL. So you could have different threads updating GPU memory or calling kernels on the GPU. And it's the only one that has supports the full set of the GPU of compute and graphics. CUDA and OpenCL only support compute, and OpenGL only supports, or mostly supports, graphics. Yes, that's it. Any questions? Yes?
So, not having looked at the Vulkan API at all, you know, at least in the early prototypes of trying to go to essentially compile Julia code to LLVMIR to CUDA, you essentially had to write what looks a lot like OpenGL code in Julia, right? Explicit, aware. I'm even now. It's been long enough since I've done this. I'm forgetting the precise variables, but basically sort of the 3D pointer addresses that you're working with, et cetera. Is that likely to persist in that fashion for quite some time, or is that something that some of the new efforts are actually allow you to write sort of more you know, sort of Julian-looking code to perform the computations?
So if we could compile Julia to the GPU, which is the premise for that, then the code could look fairly Julian. I mean, what you're missing out on is allocations, I/O, and exceptions. But besides that, you should be able to use most of the idiomatic things from Julia. Is that answering it? Good. Yes?
Do you have a concept of how the performance differs between OpenGL and Vulkan?
So I think in most of the cases, OpenGL will be fairly similar. But then if you have a lot of draw calls in OpenGL, you can have a lot more ways to batch them in Vulkan and just execute them completely on the GPU. And it's a lot easier to parallelize, so that can make things a lot faster. And there are some things with the rasterizer and the, how the GPU actually tiles and does tiled computations. I don't know that much about it. I think that's more for mobile platforms, which is supposed to be a lot faster with Vulkan, or more manageable, pretty much. You don't really have control over that in OpenGL. Yes?
How does Vulkan compare to Apple's Metal interface? Do you have any references concerning performance?
From what I know, so the question was how Vulkan compares to Metal, Apple's Metal framework. And from what I know, Metal is a lot higher level, so easier to use. You have a better learning curve there. But it should be slower and shouldn't allow you to fine-tune things that much. And it also doesn't have this intermediate representation that you could compile to. So this part would be a lot more difficult with Metal, this whole part, yeah. I've actually not worked with it so far. Yes?
Is there a mechanism like emulation or simulation or, I don't know, public hardware or something for doing continuous integration or testing if you don't have compatible hardware for Vulkan?
So the question was if there's continuous integration or testing that you could do for Vulkan. I'm not sure how far it is there. I guess Vulkan would allow for a lot more easy ways to actually implement this on any kind of hardware. So I'm fairly positive that things will happen there, but I'm not sure what the current state is. Any other questions?